that. Okay. So a couple of things here before we get started. First thing is I was looking at the syllabus sign-in sheets, and I noticed that there was a couple of us. I don't know if it was this hour or the other hour that I have this class, but a couple of us had missed getting that syllabus or sign-in sheet on time on Sunday night. I extended out the deadline, so if you can get that finished up and turned in tonight, you're still fine. It's no big deal. I get like some of the technology stuff happens. Yes, Mackenzie? The Dropbox on PowerSchool. So there's a Dropbox for the assignment on PowerSchool, and that's where we're turning it into this time, because on occasion we'll turn stuff into PowerSchool and turn stuff into OneNote. Typically the homework, like the weekly homework assignments, all are going into OneNote, but little miscellaneous other things I might put into, have you drop into PowerSchool. And basically we're doing this just in the event that we end up going all online for the year, like tests and stuff would get turned into the Dropbox on PowerSchool. So I just want to make sure that we're familiar with that kind of process. And we'll do some other stuff along the year, or along the way here while we're still face-to-face, and turn it into PowerSchool. But I'll try to be sure that I'm clear as to where I want you to turn stuff in. Okay? And again, if there's confusion or whatever here in the beginning, not a big deal. Okay? In general, the due date to me doesn't matter that much. Okay? Within reason anyways. You know, like if you're a day late or whatever and you let me know that, like, yeah, I guess I goofed that up and put it in the wrong spot, or, you know, needed an extra day or whatever. Typically, if you just ask for an extra day to do something, it's not a big deal to me. Okay? All right. So today, we're going to start talking about actual algebra here. And to start with, I just want to talk a bit about what we remember from our Algebra 1 class, or our first year algebra class. And I know that was a long time ago because, well, last year probably most of us took geometry or something that wasn't Algebra 1. So it's probably been at least, to the start of it, your Algebra 1 class, 2 years, which is a long time. So, like, if you don't remember exactly what the name of something is, that's okay. We'll kind of sort that out and figure it out. If we can get close to it, we'll figure out what it is we're talking about. And people's Algebra 1 experiences could be very different, particularly if you took algebra as an 8th grader and your 8th grade year finishes early. You know, there could certainly be stuff that you didn't see, that if somebody took algebra as a freshman and had a whole year of it, they might have gotten to that you didn't if you left. You know what I mean, guys? And then some people had, like, you know, very good Algebra 1 experiences where they had a great teacher and they covered a lot of stuff and they remember it all and it went really well. Some people had shaky Algebra 1 years where maybe they didn't have a great, you know, experience and they didn't cover that much stuff. So, like, if people are talking about things and you're like, I don't remember that, I'll try to be, as long, while we're talking about this, clear as to, like, what kind of things I expect that we kind of remember how to do and what kind of things that we're going to do again to some extent in this course. Because there is a bit of overlap, like anything else. Okay? So, anything that you might have remembered from your Algebra 1 class? Doing anything at all? Foil. Great. So that's absolutely something that I would have expected that everybody did it to some extent in their Algebra 1 class. And foiling was an acronym. It stands for first, outer, inner, last. And it just describes to you how we multiply two binomials together. So you multiply the first terms together, and then the outer terms together. You multiply the inner terms together, and then you multiply the last terms together. And if you combine your like terms, you end up with your simplified polynomial. Now probably, yes, sir. Okay, I'll get to you in 1 second. You're on deck. In general, in your algebra classroom, you probably just did this with a linear term multiplied to another linear term. And this class, we're going to continue talking about polynomial multiplication, which is what this is a type of. But we're going to generalize and look at things that maybe aren't linear terms or aren't linear polynomials. And we'll look at some polynomials that aren't binomials, that could have 2 terms, 3 terms, 4 terms, 5 terms, and how we can what are some methods we can do to kind of do that multiplication. So this is something that, in a way, we'll kind of build off from and look at some more polynomial multiplication situations that we can deal with in this course. But this will be kind of like a starting point, as my expectation is that most of us had spent some time doing foiling to some extent and feel relatively comfortable doing this kind of a skill. Yes, sir. Factoring, great. So when we talk about factoring, probably there's 2 different types of factoring that you did in your algebra classroom. There's a greatest common factor situation, where if you had something like 3x squared plus 2x, you notice that there's an x in common with each of those 2 terms. So you could factor that 1x off. It's basically like doing the distributive property just in reverse. And my expectation would be that kind of all of us had some experience doing something like this in their Algebra 1 class, or even pre-algebra class. The other type of factoring you probably talked about was for quadratics. So if you had something like x squared plus 7x plus 10, you may have learned how to factor that into something like x plus 2 times x plus 5. Now, my expectation is usually about half to 2/3 of students remember doing this in their Algebra 1 class, but not everybody probably got this far, right? So if you see that sort of factoring, you're like, I don't remember doing that. You might not have. It's not uncommon that that's something that happens at the end, and particularly if you did Algebra 1 in 8th grade, this could be something that gets missed at the end of the semester. This is something that we'll reteach, and we'll go way past this, but we will, again, cover how to do this kind of factoring again, with the assumption that there are people in the room that have never done that kind of factoring before. Now, there's also a situation with quadratics where you might have done coefficient isn't 1, so the leading coefficient is the number in front of the x squared term. This situation is a bit more complicated, as there's not a nice shortcut like there is in the other situation. And we'll learn how to deal with that. Again, my expectation is if you did factoring with the leading coefficient is 1, probably about half of those students remember doing factoring where the leading coefficient wasn't 1, and maybe didn't really feel good about it when they did it. So, the greatest common factor I would expect that we kind of remember doing and know how to do. But these 2 things we're going to redo and go beyond, because we'll talk about factoring things that aren't polynomials, that aren't quadratic, but we can kind of think about them as quadratic. We'll kind of talk about what that means later. And then we'll talk about factoring polynomials that are definitely not quadratic, that are much bigger, and we can't even think about them as quadratic, and how we go about factoring those things, because there's some neat tricks on how you can do that. And that'll be, basically the last part of first semester, the beginning of second semester. We'll spend kind of dealing with polynomials and factoring polynomials and solving polynomials and how to deal with those situations. This is kind of the simplest version of that kind of problem. But we'll start here and reteach these techniques, and then we'll kind of build off from them and get into more and more general situations. Okay, good. So those are two definite Algebra 1 topics that I would hope that at least some of us have seen. What else do you guys remember doing? Yes, sir.
Radicals.
Radicals, okay. And by radicals, you mean probably mostly square roots.
Yeah.
And you probably talked about like like simplifying square roots?
Yeah.
You know, saying that like the square root of 8 is 2 times the square root of 2 and stuff like that. This is a topic that we'll redo again because, again, my expectation on something like radicals, probably about half of us remember doing this in our Algebra 1 class and the other half maybe not. But we won't deal with just square roots. We're going to extend this out and talk about how to do things like this with cube roots or fourth roots or fifth roots and really draw a relationship between the square root and the exponential. And do a lot more than just like a square root. But that's excellent that some of us remember seeing those. Yep. So this, again, this would be a starting point. We would do this again and then go beyond and extend this out to some other less familiar situations. So that's good. What else? There's a couple of big topics that we're probably overlooking. Yes, sir.
What was the y?
Okay, so that's the equation of a line, right? So you probably talked about graphing lines. That was probably an Algebra 1 or pre-algebra topic. And you probably wrote equations for a line. Most likely in that slope-intercept form, y equals mx plus b. In this class, I would expect that you're still able to do those kind of things. We won't spend a lot of time dealing with linear functions, though. But we will talk about, each time we talk about a new function group, we will worry about being able to graph that function. And we will worry about being able to write an equation for that function that maybe passes through certain points. So this is something that, like, in a way, this type of problem we're going to do over and over again, but not dealing with like linear functions per se. So a lot of the details change or need to be modified because the function is different than a linear function. But those are kinds of problems that we'll do again, but not dealing with lines per se. But that's good. Those are definitely two of the things that I was thinking about, was all this linear stuff is very typical or classical Algebra 1 material where you spend a lot of time graphing lines, finding the equations for lines, doing slope-related things, right? You guys all remember doing stuff like that. I think you do it in geometry for a bit too, right? And you probably did it in pre-algebra also, right? So you're probably sick of lines by now, which is good because we're not really going to do, much linear things in this course. So you get a break from the lines. Anybody else have anything that sticks out at them? Okay. I think this is probably a pretty good list of things to just kind of get our memories going about like what we've done before. In general, when I present you guys material when we're doing the lectures and such, I like to try to connect what we're doing now to something we've done in the past. In general, that's what we want to do in mathematics, is you want to take something you already know how to do and maybe modify it to a new situation. So it's not like learning something all new, brand new from wholesale. What we'd like to do is take something we're already familiar with and tweak it a little bit so it works in a broader context. And we do this kind of over and over and over in mathematics. But I try to really make that explicit while we're doing things. It's like, okay, remember when you did da-da-da-da-da? Because even things as simple as like adding and subtracting fractions or multiplying fractions, like things that you've done probably since like 5th or 6th grade. You probably spent time every year doing something with fractions. There's a whole topic, there's a whole chapter in second semester that we're going to relate back to the same procedures we did when we had to add 2 fractions or subtract 2 fractions or multiply 2 fractions. And it's a really useful building point. Or you remember long division, right? Turns out there's a topic here in first semester that's closely related to long division that we're going to relate, that it's basically the same process, but you're using polynomials to do the division instead of numbers. But the procedure kind of works the exact same way. So again, we try to connect these ideas back to things that you're already familiar with. So it's not like it's a brand new thing. It's just modifying something we're already familiar with. Okay, cool. So let's start talking about topics here, or start talking about things for this class. I wrote Algebra 2 because this is like a second-year algebra course. Whether you want to count by semesters or by years, whatever. But this would be this year. Okay, so what we're going to do is we're going to start with the fundamental algebraic object. And you might think that fundamental algebraic object would be a number, right? That's what we use mathematics on. It's not. From an algebraic perspective, a number is more like an adjective. It's describing something. What we're really talking about in algebra are sets. So that's really going to be what we're going to start with, is defining this thing called a set. So a set is a list of mathematical objects. By mathematical objects, typically we're talking about things like numbers, or ordered pairs, or functions. But you could really list like any kinds of mathematical objects. You could have shapes. You could have like slopes. You could have all manner of things that we've done algebra with, not to mention things that you guys don't even know about, like permutations or ways to arrange something, or like whatever. The key though with a set is that no item on your list is allowed to repeat. So if you have a list of numbers, you can't have like the number 7 appear twice on your list. It can only appear one time. Okay with that idea? Simple enough, right? So we'll talk about some notation then. So when I say the words when I say notation, what I'm talking about is what are the symbols that we use to kind of represent this stuff? Like in mathematics, we use a lot of symbols, we use a lot of notation. It's almost like learning another language because we have all these symbols that we introduce all the time that mean certain things. So typically, when we talk about a set, we name a set with a capital letter. So I'm going to name this particular set with a capital letter A. And then if I'm going to describe what is in this set, I'll start with an equal sign. And then I'm going to draw a squiggly bracket. We have to draw a squiggly bracket to indicate that what we're about to list here is a set, as opposed to like a tuple, like an ordered pair or ordered triple. or just like a pair of solutions or whatever, that this is a set. And let's say that the set we're talking about are just the counting numbers from 1 to 10. Okay? So that list is fairly short. So one way we can describe that set is just by writing down all the things that are in the set. So the counting numbers from 1 to 10 are just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a fairly short list. We can write that down. Doesn't take very long. That's one way we can describe a set, is you can explicitly list everything that's in it. A set like this we would call a finite set, because there are, like a countable number of elements or items in that set. Everybody's okay with that idea? Another kind of set we could talk about might be all the numbers between 1 and 10. How is that different than the counting numbers between 1 and 10? Yeah, we have to include all those decimals, right? So how many numbers are on this list? A lot. Do we have a special mathematical word for a situation like this? Infinite. Excellent. Yes. So if we talk about all the numbers between 1 and 10, there's infinitely many of them, right? Any number you pick in between there, I can give you a number that's smaller or bigger than that number all the way through, right? You say, oh, 9, I'll say 9.5. You say, oh, 9.5, I'll say 9.7. You say 9.7, I'll say, oh, 9.71. And we can do this forever, right? Anything you name, I can give you something that's a little bit bigger, a little bit smaller than it. There's an infinite number of them. Everybody agree with that? So we can't write them down as a list, right? That's not plausible, since you can always come up with another one. You die before you finish the list, and it's not a very exciting life you've lived. So we're going to have a new notation to kind of describe that situation. So we start the same way. We start with the name of our set and that squiggly bracket. And then what we're going to do is just describe what that set looks like. So the first thing we do is we describe kind of the format of the things in our set. Since the set we're describing is just numbers, everything is just going to kind of look like an X, right? It's just going to be a number, like 1 or 1.7 or 3.6244119826783. But those can all just be represented by an X, right? And then we're going to put a colon after that. This colon is just an abbreviation for the phrase such that. And then we're going to have a rule that describes how I know whether those X's belong in this set or not. So if we want all the numbers between 1 and 10, it seems like an inequality would be a good way of describing that. That would be a good rule to use. So I might say just the inequality, 1 is less than or equal to X, which is less than or equal to 10. So if I tell you a number, you can use that inequality and you'll know whether that number belongs in the set or not, right? If I say 17, you're like, that's not in there. If we say 1.6, you're going to go, yep, that's in there. And it's pretty easy to see that. Is everybody okay there? So an inequality is often a useful way to write your rule, but it's not the only way to write your rule. What if we wanted to describe the set of even numbers? Well, again, the even numbers are just a number, right? So x is a decent, is really what they're going to look like. They're just going to look like a number. But what's the defining characteristic? How can I tell if something is even or not? Yes. If it's positive, well, you can have even numbers that are negative, right? Yes, sir. If it's divisible by 2, right? That'll determine whether something is even or not. That's very good. So rather than trying to write divisible by 2 as a mathematical rule, which is maybe not so easy, we could use an equation to describe that. So it's divisible by 2, and we should say something else, though, before we get too far. So like all numbers are technically divisible by 2. Yes. So it's a whole number that's divisible by 2, right? Like 7 is divisible by 2. It just, depending on what you mean by divisible by 2, right? 7 divided by 2 is 3.5 now, but in like 6th grade, which is kind of like when you're doing your long division, what you mean is divisible and means no remainder, right? But that's a little harder to express, having remainder 0 in terms of a rule. So what we're going to do is we're going to say, okay, this is the set of x's such that x is 2 times y, where y is a member of the set of integers. So this is a bunch of notation here at the end here. This little like curved E means is a member of the set. And this weird looking Z with the double bar on the diagonal is the set of integers. And do you guys remember what the integers were? They're just the positive or negative whole numbers, including 0. So what this is saying is pick any integer you want, like 7. If we multiply that by 2, I get something that should be in the list, or should be on my set, right? So the fact that you're taking a whole number and multiplying it by 2, the fact you have a whole number times a whole number, guarantees you're getting a whole number. And because you've multiplied it by 2, that guarantees that it's going to be divisible by 2. Right? So all of these x's are going to be even numbers guaranteed. Everybody agree with that? Okay. What if we wanted to do Yes, sir. Well, are the odd numbers divisible by 2? And if we just took what we had here and divided it by 2, some of the integers are even, right? So you're on the right track, though, of wanting to modify what we had before. Mackenzie? You trailed off at the end. I missed. You divide by 2, but you don't get a whole number. Okay. Is there an equation that we can write that guarantees that happening? Okay, let's say we have an even number, like 2. What's the nearest odd numbers to 2? 1 and 3. How did you get to 1? Subtract 1. How did you get to 3? Add 1. So let's do that, one or the other, to what we had before. What if I just have 2y plus 1? Right? If I take an even number and add 1 to it, what am I always going to get? An odd number, right? Would it have worked if we subtracted 1? Sure. In fact, you could have added 11. If you add any odd number to it, it'll work. There's nothing magic about 1, but that's a typical way to represent that. Do we feel okay about writing the rules here? So these ones where you have to write an equation are maybe some of the trickiest, but they're not so bad. What if we wanted the set of perfect squares? What do I mean by a perfect square? What's an example of a perfect square? What kind of a number? What was that? I heard somebody say something. 16 is an example of a perfect square because it's 4 squared, right? Or 9, exactly, which is 3 squared. 36, which is 6 squared. We get a feeling for what a perfect square is. Okay? So again, these are just numbers. And what should we be doing here? Y squared. Okay? But what does y have to be? Doesn't have to be even. Can it be a decimal? No, it has to be like a whole number, right? Is everybody okay there? Does it matter if that number is negative? No, right? Because negative 2 squared is still positive 4. Still a perfect square. So, no problems there. Okay. So that gives you a little flavor of writing those rules. They're usually not too bad once you kind of get the hang of it. But you have to think a little bit about like how to express that, right? And these guys are all examples of, do this real quick. Infinite sets, because each one of these has an infinite number of things in it, right? There's infinitely many numbers between 1 and 10. There's infinitely many evens or odds or perfect squares, right? Anytime you give me a perfect square, I can find you one bigger just by, taking the square root, adding 1, and then squaring it again, right? So the next perfect square after 36, well, the square root of 36 is 6. I'll add 1, that's 7. 7 squared is 49. And I can do that forever, right? Okay. So let's talk a little bit about some special sets. So there's 5 special sets that we're going to talk about here. They're special in the case, or in the sense that they're kind of fundamental to algebra, so much so that they each get a special name and a special symbol to represent them. So rather than using like any old capital letter, we're going to give these sets their own special symbol. The integers are actually one of those sets, and that's the special symbol for the integers there. We'll get to it in just one moment. The first special set, though, that we're going to talk about is called the natural numbers. And the special symbol we use for the natural numbers is this capital letter N, but we put a second bar on the diagonal part of the N. And the natural numbers are just things, are just 0, 1, 2, 3, yada, yada, yada. When we write 3 dots like that, what does that mean? What's that? Right, to be continued. It means continue along in this pattern forever, right? That symbol actually has a name. It's called an ellipsis. Maybe that's not how you spell it, right? It's that. I don't know, I'm a terrible speller. If you see me spelling things wrong and you know that it's wrong, and you do know how to spell it, let me know. But I'm going to warn you right now, not my strong suit. Funny thing about the natural numbers, as a mathematics community, there's no consensus on whether the natural numbers include 0 or not. Which is strange, but you have to realize that mathematics, a lot of different parts of it, were done at different times in different locations by peoples that didn't really communicate with one another. And so you have like whole pieces of mathematics that are built around like the natural numbers including 0, and other peoples that did the same kind of thing, but the natural numbers didn't include 0. And so it's like I don't want to have to go back and like adjust everything we've done to include this or not include this. So there's still some conflict about whether that 0 should be there or not. In general, in a high school setting, when we talk about the natural numbers, we're probably including 0. In computer science, anybody in this class taking a computer science class right now or in the past? One of us, maybe. You'll know if you've done any programming that the computer indexes things in a list starting with 0. So the first thing in the list is the computer calls the 0th thing on the list. And then the second thing is actually the first thing on the list, et cetera, et cetera, et cetera. So the computer uses 0 or the natural number 0, 1, 2, 3, 4 to do its indexing. However, when we talk about like most advanced mathematics settings, we're probably not including 0, because typically, again, what we use this for is indexing. And we just like the first thing to be indexed with a 1, the second thing to be indexed with a 2, etc. Now that kind of a detail I would never test you on. It just kind of, we're having a conversation, it's kind of interesting, you know. As long as you can recognize one or the other as the natural numbers, you're good. Okay. Next up is the integers that we had mentioned there just a moment ago. So again, the integers have this funny symbol that looks like a Z with 2 bars on the diagonal. Or it kind of looks like, the way I end up drawing is I draw a 7 and then another 7. It's kind of the way, or an upside down 7, I should say. But it doesn't really matter how neat you are with that, as long as it kind of looks like a Z with two bars on the diagonal, it's good enough. As an interesting aside, Which set is bigger, the natural numbers or the integers? Which has more stuff in it? Yes, sir. Yeah. So I'm not talking about totaling up all the numbers in it. I'm saying which has more items in the list. So you say the integers because it has the negatives and the natural numbers doesn't, right? What do you guys think? They're both infinite. Does that mean they're the same? So here's something that's surprising. So they are both infinite. They are the same size, but not all infinite sets are the same size. Let that sink in for a second. These are both infinite, and they are both the same size. They have the same number of things in their list, which seems odd because one has negatives and the other doesn't. And you're telling me there are different sizes of an infinite, but these two are not different sized infinite, even though it seems like one has stuff the other doesn't. They are the same size. How would we prove that? It's actually a clever trick. So if you want to do counting, I have two piles of things and I want to show that we have the same number of things in each pile. One way you could do it, you should count pile A, see how many are there. You count pile B, see how many are there, and see if they have the same number of things, right? What's another way you could do it that doesn't involve any counting at all, since we can't count an infinite set? What if we just paired things together? If I took one from this pile and one from this pile, threw them aside, one from each pile, threw them aside. If I get down to the bottom and I'm able to pair everything in this pile with one thing in this pile, they must have the same amount of stuff in them, right? We did no counting to do that, right? All we did was pair everything up so that everything in one pile paired to exactly one thing in another pile, and vice versa. Yes, sir. So when we say pairing, we're not going to add them, right? We're just going to say, like, this one pairs up with this one. Like, we're connecting them together. We're not actually adding. Okay? Now, you still might say, okay, well, I'll pair 0 with 0, 1 with 1, 2 with 2, 3 with 3, but I have nothing to go with the negatives and the integers, right? Still seems like a problem. You're not doing the right kind of pairing. So if I look at the integers, I have two kinds of numbers that I have to worry about, right? I have positives and I have negatives, both of which are infinite sets. Everybody agree with that? Look at the natural numbers. There are two types of infinite sets in the natural numbers. It doesn't matter which one you want to use. Let's use the one with 0. Well, we need two infinite sets from the natural numbers, right? Like from the integers, I have an infinite set with the negatives and an infinite set with the positives. Can we find two infinite sets in the natural numbers? I'll give you a hint. We've already talked about the two sets that we need today. Yes. Evens and odds are both inside of the natural numbers. They're both infinite, right? So what we're going to do is from the natural numbers, we're going to take 0 and pair it with 0. We're going to take the evens and say we'll pair the positives. We'll take the odds and we'll pair those to the negatives. So like 1 is going to go with, or 0 is going to go with 0. 2 would go with 1. 4 would go with 2. 6 would go with 3, etc. And then 1 is going to go to negative 1. 3 is going to go to negative 3. Or I'm sorry, negative 2. 5 is going to go to negative 3. And so on. So I've taken everything in the natural numbers now, right? I have 0, I have all the evens, I have all the odds. And they're going to go to everything in the integers, right? I'm going to get all the positives, all the negatives, and I'm going to get 0. So what can we say about these two sets? Must be the same size. Because I can take I have my two piles, I can pull off a pair at a time, and I can do that, and there'll be nothing left in either pile. Everybody okay with that?
Is that like relevant?
This is an aside. I would never expect you to come up with this argument on your own, or even repeat this argument for me. This is interesting, and it's cool, and it's kind of like a whoa moment. But it's not something I would expect you to be able to do on your own, right? Like, this is cool and interesting. We're having a conversation, and hopefully this makes you think about mathematics maybe in a different way than just computation. Then that's why we're doing this. Okay? But fair question, and feel free to ask. Like, this seems really pretty difficult for me, and not like am I going to have to be able to do this again on my own? Like, that. Those are fair questions. Okay? And no, to answer it. No, you would not. Okay. Everybody feel, even if you don't see, couldn't come up with this on your own, after we've talked through it, you can kind of see how we're going to say that they're the same size. Yes? Now, that's really clever on doing that. That's not obvious at all. Okay. Next set is the rational numbers, which we abbreviate with this Q with an extra vertical bar inside the circle part. And here our definition for our set of rational numbers looks a bit cryptic, right? This doesn't seem like super understandable, but let's see if we can kind of parse this out. Because the symbols that are involved here are all symbols that we should recognize now after today. So Q is the set where the things in the set look like P over Q. What does P over Q look like? Fractions, okay? And then we know the colon is the such that. And then P and Q are members of the integers, right? We know what that little string of symbols is. What is, in terms of the fraction that we've written down, what part of the fraction is P? The numerator. And what part of the fraction is Q? The denominator, okay? So what we're saying is that these fractions don't have decimals in the numerator denominator, which is normal, right? That's not how we typically write a fraction. And they don't have like a fraction inside of a fraction, right? Everybody's okay with that idea? And then we have one last piece. We have that q cannot equal 0. Why do we have that? What part of the fraction is q? Denominator. What happens if a denominator of a fraction is 0? You're dividing by 0, which is impossible. It's undefined. Very good, right? If you want to hear a funny story, ask Siri what 0 divided by 0 is. It's kind of cute. It takes 15 seconds, but okay. So that's basically what that string of symbols is saying, right? So at first glance, you're like, what the heck does that mean? But if you just kind of go symbol by symbol, it's kind of like a decoding exercise, like you're in a foreign language and you're trying to figure out what a sentence says, and you go word by word. We just kind of went symbol by symbol and translated it into English, and it's like, oh. Basically, you're just describing normal fractions, the fractions that we're all familiar with, right? Everybody's okay with that? Now, it's a little bit more subtle than that, because we know fractions, oftentimes fractions are equivalent, right? So for example, the fraction 1/2 is the same as the decimal 0.5, right? Everybody's okay with that? So would 0.5 be in this set? Yes, because it can be represented as the fraction 1/2. Okay? So here's the question then. So we know that decimals can be some decimals can be represented as fractions. We've just shown it with one. Oops. So are there decimals that cannot be represented as fractions? What do you guys think? If you think you have one, let me hear it, and we'll see if we can turn it into a fraction or not. Yes, sir. Go ahead. Like this? I can turn that into a fraction. So the way I'm going to think about this is I'm going to think about it as 4 plus 0.34 plus 0.0034 plus 0.00034, like this. Everybody okay there? I'm going to keep the 4 there, and this part is what's called a geometric series. This is something we'll learn about in second semester. But what it basically comes down to is I can let's write it that way. Take the sum of all that stuff together is going to be the first term times 1 over 1 minus this common factor. So each time I'm multiplying by 0.01. And this will spit out as a fraction. Now, so let's continue it out so you can see. So that's going to give me 0.34 over 0.99. And I can convert that into a fraction just by multiplying the top and bottom by 100. So I have 4 plus 34 over 99. And then I can make a common denominator and finish that off, and it turns into a fraction. So that one, it works, right? We can get that one into a fraction, even if it's infinite repeating decimal like that. And I'll tell you that anything with an infinite repeating decimal, we can do the same trick to, right? Doesn't matter how long the repeating section is. If it repeats over and over, I can do this. Excellent. What about pi? What do we know about pi? It's infinite and doesn't repeat. So, can we write pi as a fraction? No. So our canonical example of a number that cannot be written as a fraction is pi. The next most common example would be square root of 2. And in fact, any radical that doesn't simplify down to an integer is also going to be impossible to write as a fraction. We call these numbers irrational. I heard somebody say that when we mentioned pi. So there has to be something bigger than the rational numbers, because we've got some stuff that's not rational numbers here, right? So the next biggest one, or the next one out, is the real numbers that we abbreviate with the symbol R that has an extra vertical bar. So we're just going to say that the real numbers are the set of x's such that x has a decimal expansion. Basically, that you can represent it as a decimal. So does that include the fractions? Yeah, how do I represent a fraction as a decimal? You just do the division, right? You take the numerator and divide it by the denominator, and it's going to spit you out a decimal, right? Just doing the long division that you did in elementary school. So that's no big deal. So is there anything that's not included in the real numbers? We'll hold on to that for a second, because let's ask a different question first. So another aside. Which is there more of? The integers or the the integers or the rational numbers? It's a little harder to see here. They're both infinite, right? But is one infinite bigger than the other? They are also the same, which is really surprising. This result is non-trivial. We're not going to even discuss kind of how you'd go about doing it, because it's actually quite complicated, the mapping. But it involves like making an array of the integers by the integer. So you have all the integers here and all the integers here. And you end up like looking at the ordered pairs in each of the places, and you have to cross out the duplicates that are like reducible fractions and things that are, but you can do it. It ends up like you zigzagging through diagonally to make the pairing, but you can do it. A mathematician named Gregor Cantor did this, who's very famous. prominent mathematician that did a lot of important work in set theory. Okay. So that's still the same. So how about, which is there more of, the rationals or the reals? Here it's finally different. Here there are more real numbers. Well, it's quite, again, this is a very difficult proof, but what it basically comes down to is the easiest way to do this is instead looking at the natural numbers and trying to map it onto the interval from 0 to 1. Is the easier way of kind of trying to do this. So if you can't even do that, you can't get to the real numbers, right? Because 0, 1 is a subset of the real numbers. Everybody okay there? No, R is different. And Z and Q are the same size. Okay. R is the bigger one. But what it comes down to is you basically are going to try to pair these up with like decimal expansions. Kind of like this. But no matter how you do that, if you add up all the decimal expansions, you get something that's not on your list. So like, there's really no way to do that, but that's the gist of the argument. It's much more complicated than that, way beyond the scope of this class, but that's kind of the argument, is that you can't make a pairing there. And in fact, if we just wanted to do which is there more of fractions or irrational numbers. Surprisingly, there are more irrationals. In fact, between any two rational numbers, there are infinitely many irrationals, which is like kind of mind-blowing, right? Like between 1/2 and 1/3 on the number line, the little tiny sliver, infinitely many irrationals. Again, I'm not going to prove that. That's a quite complicated proof, but it's surprising and gives you an idea of like how much is going on that we don't really see in a high school curriculum, right? Like you barely talk about irrational numbers, and there's so many of them, which is really strange to think about. Like, how are they this common and we just don't run into them all the time when we're doing things, right? Okay, on for the last set. The last set is the set of complex numbers. There is one more out from the reals. So the set of complex numbers we abbreviate with the C with an extra vertical bar in there. So the complex numbers are of the form a plus bi, such that a and b are real numbers, and I is equal to the square root of -1. Has anybody talked about complex numbers before in their Algebra 1 class? It's pretty rare. Maybe 1 or 2 kids a year says yes when I ask them that. So don't feel bad if you don't. We'll talk about these in great detail later on this semester. So I'm not going to spend a bunch of time kind of explaining what's going on here because it needs a little bit of context on what's going on. So I want to talk about a relationship between these 5 special sets. So we're going to start with a definition. This definition is called the subset. And the symbol we use for a subset is like that sideways union symbol with a bar underneath it. We say A is a subset of B if everything in A is also in B. So, if I think about the natural numbers, you have 0, 1, 2, 3, 4, etc., right? If I look at the integers, do we have 0, 1, 2, 3, 4, etc. in the integers? Yeah, right? So we can say that the natural numbers are a subset of the integers. Everybody's okay with that? Now let's talk about the integers and the rational numbers. The integers, things like -3, -2, -1, 0, 1, 2, 3. Can I represent those numbers as fractions? Yeah, how do I do it? Just put them over 1, right? That'll do. So everything in Z is also in Q then, right? So those are, Z is also a subset of Q. And then by extension, N is also a subset of Q, right? Everybody's okay with that? That seems natural there, doesn't it? Okay. Now we'd said that all the fractions we can rewrite as decimals, right? So all those fractions then are definitely real numbers. And the last thing to sort out is, are the real numbers also complex numbers? Let's go back and look at that complex numbers definition real quick. So all these complex numbers look like A plus BI, where A and B are real numbers, right? Well, 0 is a real number. What if I let B be 0? That would give me something that looks like A plus 0I. What's 0 times anything? What's anything plus 0? Itself, right? So that would just turn into A, right? And what is A? Just a plain old real number. Everybody agree with that? So are the real numbers in the complex numbers? Sure. All it just means is that that B part will be a 0. And then we have just like a regular old real number. So yeah. Oops. The complex numbers contain the real numbers. So if you are a visual person, oops. You can visualize this. Oftentimes we'll visualize sets as just like a circle like this. But this subset relationship is basically just each of these sets is progressively a little bit bigger and contains everything previous, right? So are we all okay with that idea? Cool. This seems like a good place to stop here. I don't have, at this point, we haven't done a whole lot. We just kind of done some definitions and some notation and talked about some cool, interesting stuff. So I don't have any homework for you guys to work on today, which is fine, right? You guys don't mind, I'm sure. So yeah, thank you. I like the participation. You guys, I feel like, thought pretty hard about some stuff. You had a lot of good answers and some good suggestions, and I like the participation. So good job today, and kind of keep it up. But that's it. Those of you watching at home, we're all done. So you guys can head out to your next thing, and everybody else here, you can hang out for 5 more minutes till it's time to go.